All right, hi everybody. In this video, we're going to look at an introduction to the topic of autocorrelated errors or serial correlation in an OLS model. We'll follow chapter 9 of the Studenmund textbook, but virtually every intro econometrics book has a chapter on autocorrelation or serial correlation. And we're going to introduce the topic, look at how to model an autocorrelated error, what might be causing the problem, and that'll lead us to follow-up videos where we'll look specifically at what are the implications of estimating a model with OLS, how to test for it with examples in Stata and R, and then how to quote unquote fix the problem also with some data examples. So to begin at the beginning, right, recall our classical linear regression model or Gauss-Markov assumptions regarding the error term, right, that U error term from a regression. Note, and we'll get into this specifically in a minute, that we're using the time series subscript, right? So Y sub t, X sub t, U sub t. Those are all observations at a specific time period denoted t. And we're also assuming a simple regression model, but for the most part, everything we'll look at will generalize to a multiple regression model, right? But with that error term, of course, we expect it to be a truly random outcome each period with a zero expectation. We expect it to be uncorrelated with our explanatory variables, have a constant error variance, call it sigma squared, and we expect each observation of the error term to be uncorrelated with every other observation. So correlation between UT and US should be zero for any T and S representing different observations. And again, this sounds like an obvious assumption, and it follows directly from the idea of the error term being a random outcome. Knowing one observation's value of the error term shouldn't give us any information about what any other observation is going to be, because each should be entirely independent and random. And we can think about it, this idea of each observation of the error being a random draw from an underlying independent sampling distribution. So when we have a violation of this assumption, it's a pretty big deal, right? That now each observation of the error term can no longer be truly thought of as a random independent outcome. This period's value of the error term gives some information about the next period. A non-zero correlation means there is some predictability there. So the error term, therefore, can no longer be thought of as truly a random outcome. So it's a fairly fundamental change in our view of the regression model when we have a violation of this assumption. So our plan of attack here, we will look at different kind of ways of categorizing, if you will, autocorrelation, different types of autocorrelation, how we can model an autocorrelated error within a simple regression framework, what might cause an error term to be autocorrelated. In other words, what scenarios, what data types might lend itself to this problem. That's going to be our set of topics for this particular video. Then we'll get into the why we care, what are the consequences of estimating OLS with an autocorrelated error, how do we test for it, and how do we correct it. So those are coming up in future videos. So for our kind of categorization, different types of autocorrelation, well, usually the first thing that we want to think about is what is the so-called order of autocorrelation? Okay. And here we're thinking about how far away, quote unquote, an error term is that will still give information for a given observation, right? So in general, we think of U sub t and U sub s, right, as any pair of error terms. The notation, right, is telling us it's time series. So period t is today, period s is sometime in the past or the future. But it can really be any two observations in a cross-sectional data set. It could be firm 1 and firm 2, right? The most common form, and this should make sense, right, is going to represent correlation amongst adjacent error terms or the nearest neighbor error terms. And again, in time series data, this is going to be really easy to see, right? So if you have daily observations, we're thinking about how does a random shock today influence the error term tomorrow? How does the error term yesterday influence today? If you had monthly data 1 month prior, how does that influence today? So it would be the correlation between t, the current period, and t minus 1, the 1 period lag, or the adjacent period. We'll look at kind of an example when we get to the causes of what this would mean in cross-sectional data, non-time series data, but the idea is the same. Some way of defining distance, right? Or a nearest neighbor effect. So with first order autocorrelation, we're limiting ourselves to this distance. Only the adjacent error terms directly affect each other. And when we get into testing and correcting, that's the assumption that we're going to be making, that we're limiting ourselves to that first order. But higher orders can definitely be, you can definitely run into that in your data. Another way we can categorize our autocorrelation is by the sign of that correlation. If we have positive autocorrelation, well then adjacent error terms are going to tend to look alike. They're going to tend to share the same sign. A positive error is going to beget a positive error tomorrow. And that's going to come across in the data as simply a positive correlation coefficient or a positive covariance. And our first step in testing is actually going to be visualizing the data. And when you see a clustering pattern of the residuals of the error term, that's going to be indicative of a non-random behavior, and B, a positive correlation. Error term is positive today, its neighbors are likely positive. It's going to form that cluster effect. A negative error is going to bring its neighboring error terms to be negative as well. Another little cluster. And it may end up, obviously this is a stylized representation, but it may end up looking something like this, where each observation of the error is not just a random occurrence, but part of a little localized cluster. So positive errors clustered together, negative errors clustered together here. If you see that when you run a regression and pull up a visual of your residuals, that's telling you we have a problem, right? That Gauss-Markov assumption of a purely random error term is not being met. It might also look something like this, right? So looking out for that sine wave pattern as an indication of positive autocorrelation. You may see negative autocorrelation where one observation of the error is going to beget the neighboring observation with a likely opposite sign. So a negative error today might predict a positive error tomorrow between t and t minus 1. And this is going to be much less common, also more difficult to pick up in the data because it's going to represent this mirror imaging pattern. So it can actually look pretty random where the sign of the observations are flip-flopping each time period, but it's still going to be a pattern, a non-random outcome that shouldn't be there, and it might look something like this, right? So yes, there's no clustering happening here, but there's definitely predictability, negative to positive to negative, etc. Okay. So once we have this idea of what an autocorrelated error represents, what it might look like in the data, depending on the sign, we want to be able to incorporate this information into our regression model. And there's lots of different ways we could do this. We're going to look at one specific model of an autocorrelated error term, the so-called first order autoregressive linear model, which we'll refer to as the AR1 model. So autoregressive of order 1, meaning it's just the first lag, the adjacent error term that's going to be relevant. Okay. So to kind of parse that title here, the current error term ut is a linear function of its autoregressive term. It's regressing the error term on itself, and it's first order telling us that it's only that one lag that's going to be the explanatory variable. And then, like any good regression model, we're going to include an error term. So this is quite a different way of looking at the behavior of the error term. We're no longer just saying, oh yeah, it's a random, possibly normally distributed outcome. Now the error term, each observation, is itself a dependent variable. It's a predictable outcome. Really no different than how we treat our y variable in a regression model, where we have y equal to b0 plus b1x plus ut, and we use that information to predict y. Well, here, the error term, ut, is equal to some function of its own lag. So put this in quotes, right? Playing the role of the dependent variable, the y variable, is the error term. Playing the role of the x variable is the error term's lag, ut minus 1. Now, playing the role of the b1, or the slope term, is this guy, this Greek letter rho. And then there's also a truly random component here, the e sub t. Obviously, all this notation, it doesn't really matter what we call it, but we'll try to be consistent here. But the important thing is, right, that we're able to model the behavior of this error term as a prediction function. That's what we're doing here with this AR1 model. So that new item that we added here to our notation vocabulary, right, the Greek letter rho, that's representing the so-called autocorrelation coefficient. And it is going to be a correlation coefficient, right? It's going to be correlating the lagged error ut minus 1 with the current error u sub t. And as such, it's going to lie in that range between -1 and 1. And the beauty of it is, if we know what that rho term is, if we're able to estimate rho, we know almost everything about the nature of the autocorrelation problem in our data. Right? When that rho term is negative, less than 0, well, then our error term has negative autocorrelation. Positive error yesterday correlates with a negative error today. When that rho term is positive, positive correlation between ut minus 1 and ut, our error term suffers, quote unquote, from positive autocorrelation, positive AC. And if that rho term is 0, well, then there's no relationship between lagged error and current error, and no autocorrelation. So another way to kind of summarize the classical assumption, the Gauss-Markov assumption, that the error term should be entirely random, is that we're assuming rho is 0 in the autoregressive of order 1 equation. The other thing that we added, right, was, again, a new error term. So it's an error term that helps predict another error term. So this ET error term at the end of that AR1 equation, now we have to make another assumption, right? We're going to assume that this error term is the perfectly behaved Gauss-Markov error term. So it should have all of our desirable properties: 0 mean, constant variance, normal distribution, and not autocorrelated with itself. So the assumption is that if we dig down far enough, there is a truly random, well-behaved error term. It's just not the original regression error term, the UT in this case. Okay, so now we'll look at the likely causes of serial correlation or autocorrelation. And again, think about this as just a list of scenarios that might make this situation more likely to occur, okay? And the first item on the list is actually the one that's most problematic for non-time series scenarios, so panel data or cross-sectional data. And we can think about this as kind of geographic or spatially based autocorrelation, where we'll have regional cross-section data, or at least data that acts as if it's location specific. And we're thinking about a random shock in one region, region I, may influence outcomes in region J. So there's these externalities or spillover effects across neighboring geographic regions. Right? So we're really thinking about this in terms of, say, a contagion effect, or like we said, a spillover effect across countries, across firms, across industries, whatever the case may be for your particular data. Right? So an example, If Europe experiences a random shock, say a negative shock to the overall economic health of Europe, well, because the US is a trade partner and capital flow partner, the US economy would be affected as well. So a random shock in one period has an effect on an unexplained variation in the dependent variable in another observation. That is autocorrelation. Maybe unnecessary, but just to get kind of another example here, where we might see an example of negative spatial autocorrelation in bilateral FDI, foreign direct investment flows, right? So we're imagining FDI outflows from the US, and say there is an unexplained random positive error term in the flow from the US, say, to Thailand. Well, for any given period, if there's a fixed amount of financial capital that can be used in foreign direct investment, it's got to come from somewhere. So that might be associated with an unexplained negative error, say in the FDI outflow to Mexico. So we'll have one positive error begetting a negative error on another observation. And what does that mean? A negative rho in our AR1 term, a negative correlation coefficient between the two. So you can think about this in terms of crime reporting at the county level, say in the US. If one county has a spike in crime, well, is that going to have a spillover effect into neighboring geographic regions? If so, you have spatial autocorrelation and the error term is no longer truly random. So lots of scenarios where this can come up. The most likely scenario, of course, is going to be with time series data. So we're kind of putting a lot into this slide, but the idea is that if you have an inertia effect or a sticky, slow adjustment over time in your dependent variable, it's going to end up having these residuals, right? Mistakes in your prediction model that have a shared characteristic amongst neighboring observations. So the analogy you often hear, right? Say you're trying to predict GDP, changing output for the economy as a whole. Well, it's going to be changing very slowly in reaction to stimuli. The model is going to be predicting that GDP should be going up because all of the X variables are predicting an increase. And it's going in that direction, but much more slowly than the model predicts. Those mistakes that are made along the way as that adjustment occurs are all going to be of the same sign. You're either going to be over predicting or under predicting each period. And what does that mean? Correlations amongst those error terms, non-randomness amongst those error terms. So anytime you have a model where a sticky price scenario makes sense, right? Either literally predicting a price or any slowly adjusting outcome, we're going to be in exactly this scenario. So again, this slide may be a little overkill, but just kind of the visual of what you might be thinking about. Say we're predicting the price, say the price per barrel of oil, and we have as X variables in our regression, kind of all of the supply and demand determinants, and our model is initially predicting, right, the initial equilibrium, say at price level P1, and then something happens, right? Income expectation, something changes, and it shifts the demand curve to the right. And of course, our model is going to predict an increase in price from equilibrium P1 to P2. But what's actually going to occur is that prices will slowly adjust over time, right? The old story, as suppliers react to changes in inventories, in this case, a shortage at the original price, prices will eventually work their way up. But along the way, our model is going to be consistently wrong, right? So tracking prices over time, the first little function here with the jump up at the time period where the demand shift occurs, that represents our predicted prices. Think of that as the y hat in our regression, whereas actual prices will be tracking slowly up from the original P1 to the new value at P2. So what does that mean? Each period, this gap is going to be the residual. the y minus the y hat, and they're all going to be the same sign. They're all going to be negative, right? So the solid line is the y hat. The little dots are the actual values of y. So y minus y hat is going to be negative, and we're going to have that cluster of observations. That's usually what's happening when you see that in the data, that there's this slow to react dependent variable. Therefore, the model is going to make the same mistake multiple adjacent periods. So a positive autocorrelation will result. Okay. Other ways we can have a model with autocorrelation, and this one maybe is not so obvious, data manipulation. So I'm thinking mostly about seasonal adjustment and smoothing algorithms that are applied to time series data. And as the name implies, right, what these do is they smooth out random shocks, right? And in so doing, they make the adjacent observations take on the same characteristic, right? So think about a 7-day moving average calculated, say, for stock market prices. If one day in the week has a higher than normal outcome, smoothing that out, averaging it out, is going to make the adjacent values take on that same characteristic, higher than they should be. And what is that going to do? It's going to have them with a shared sign of the residual. Same idea. Okay, so there are times and scenarios where a smoothing algorithm or a seasonal adjustment is going to be useful, but it may be introducing some level of serial correlation or autocorrelation into your data. Another way we can do this is through mis-specification, right? So usually when we think of mis-specification, we're concerned about omitted variable bias. It turns out, I mean, that's the big item that we should be concerned about, as we'll see. But if we omit an important variable that is itself following an autocorrelation pattern, its past values predict its future values, then, right, remember what causes omitted variable bias is that the behavior of the omitted variable is absorbed into the error term. So if that omitted variable has an autocorrelation pattern, now your residual is going to take on that same behavior. So this would be, the case where if we ran the perfect model, perfectly specified, you might not have autocorrelation, but due to omitted variables, we're introducing it. And since realistically every regression contains some level of omitted variables, this is always going to be a potential issue. So, sorry, again, a kind of a busy slide here, but the idea is if the correct model, right, is predicting y as a function of two variables, x and z, but for whatever reason, we don't have the data on z, we forget to include it, we omit this variable z, and variable z, like many time series variables, has its own autoregressive pattern. Past z predicts future z very well. Well, then we run the model without z, so just x influencing y. The error term in this misspecified model is going to take on the entire variation of the original random error, ut, and the influence of z. So there you have it. Vt is a function of zt. Zt is a function of its own lag. We've introduced this dynamics into the misspecified error. So even if ut was well behaved, the regression error for our model will be autocorrelated. One more item as far as functional form or as far as misspecification is concerned, causing autocorrelation, is functional form misspecification. That's where we're running a model that is linear typically, and it should be nonlinear. That mistake not only will result in a less accurate prediction, can also introduce autocorrelation. So think about the case where the true model should be, say, a diminishing returns, a nonlinear quadratic, and you try to fit a straight line through the data. The mistakes that your prediction are going to make are not going to be random. there are going to be shared mistakes, the same characteristics of those residuals in neighboring observations. And what does that mean? That's autocorrelation. A picture being worth 1,000 words might look something like this, right? Looking at the data, the little dots representing actual observations of Y. And just imagine we look at that and we say, oh yeah, let's just fit a straight line as our prediction model through that. Well, all of these residuals, right, this looks exactly like the little plot we had at the beginning, are going to be a cluster of shared positive errors, actual values above the prediction. All of these are going to have negative errors, so positive autocorrelation. Okay. So yet another reason to do your homework and make sure that you are fitting the right functional form to your regression model. So just as a quick piece of vocabulary here, the form of autocorrelation due to omitted variables or mis-specification, meaning it's our fault, right? The researcher did something wrong and introduced autocorrelation where it wouldn't have otherwise been. That's referred to as impure autocorrelation. It's not part of the data generation process. Right? It's rather due to the specification used. So that form of autocorrelation we can actually fix, like we said, by doing our homework, by making sure we get those specification criteria correct. And if you're concerned about this, especially if you have a large sample of data, you have a lot of observations, you can be a little bit more generous, quote unquote, in specification. So if you're not sure if you should have X and X squared, it's kind of borderline, maybe include that X squared value. If you're not sure if a Z variable belongs in the model, it has, borderline significance, go ahead and include it. Again, if you have a large enough sample, because you'll be both avoiding omitted variable bias potentially and mitigating autocorrelation. Okay. Again, with smaller samples, you're going to have to be more judicious, but that's one kind of lesson that can come out of this. Okay, so next up, we'll look at why we should care, how we can test for it, and how we can fix it. Thanks.